Good day. We're going to start thermal systems now. These are systems that store heat and regulate the flow of heat. So you might think of things like a thermometer, an oven, or refrigerator. Uh, these systems generally require partial differential equations to solve. So we're going to be definitely making some approximations here. The key variables, temperature would be in Kelvin. That's Celsius is equal to Kelvin minus 273.15. So Celsius plus 273.15 would give us Kelvin. Heat flow in watts as normal. We'll note that we're going to want to put things into dynamic equations. So you have sort of a nominal temperature background plus a perturbation around it. We'll be focusing on the perturbation. Or a heat flow, you have a nominal heat flow and then the perturbation around it. When we're looking at thermal systems, the analogies we've had: force is like current, is like heat. Heat flows, it's a current. Okay, what drives force was displacement. What drives current is voltage, and temperature differences drive the flow of heat. So these are our analogies if you want to compare them. There are only two types of elements in thermal systems that we're going to consider. We have capacitance, which is the heat flow in minus the heat flow out is the heat stored, heat flow stored. So we have type equals C theta dot, C being capacitance. Okay. And if we're looking at capacitance, it's equal to mass times specific heat. Okay, those are the units we have there. Then we have thermal resistance. So R times the flow of heat is equal to the temperature temperature difference across the thermal resistance. And so we have R is equal to the distance of or length that the heat has to flow, the cross-sectional area, and alpha, the thermal conductivity. So D divided by A alpha. The equations presume that the body, the thermal resistance body, is not storing any heat, and thermal resistance pertains to conduction. So as you have your course in heat and mass transfer, there are two other modes: radiation and convection. And especially with respect to radiation, we are not considering that at all in this course. All right, so a couple of quick examples to get us started. So first example, we have a temperature. The top and bottom are insulated, and we have two bodies with their own distinct resistance characteristics. We have R1, R2, and on the other side we have theta 2, a new temperature. All right, so the flow through here would be, we'll model the temperature at this interface. So we're going to model this as, so we have a temperature here, there'll be a temperature at the interface, and then there's whatever temperatures at the end. So we don't know what that is, but so we'll just call that theta B. So the heat flow through here, we'll assume theta 1 is hotter than theta B. Okay, so then we would have the heat is 1 on R, all right, theta 1 minus theta B. That would drive heat this way. Now, if it turns out this was hotter than that, it would go the other way. And that just becomes a negative. So just let the signs work for you. Likewise, R2, the heat flow, whatever goes through here, can't be stored, so it's got to keep on going. So we'd have 1 on R2, theta B minus theta 2, all assuming the heat's flowing this way. Again, if this is hot, if this is hotter than this, it'll go the other way. And then this will wind up being negative. You'll know your assumed direction was wrong. Nothing wrong with that. All right. So if we, this theta B we really don't care about. So let's multiply this R1 up, and we'll do the same for the R2, and we'll solve the equation for theta B. So if we multiply through R1, So we have R1Q. I'll bring the theta 1 to the other side. Likewise, we'll have R2Q, and we'll bring the theta 2 to the other side. But no, we need this to be negative, so we'll adjusting the signs accordingly. All right. Well, now we can, looking at this must equal that. We have our minus theta b in the middle. And so we'll just equate these two on the outside. So we can bring the r's to the other side, bring the theta to the other side. And we wind up with the heat flow is equal to 1 on R1 plus R2. So they're in series, they add. Well, that's kind of what we'd expect, right? As an electrical analog, theta 1 minus theta 2. So resistors in series add. This is thermal resistors, that is. Okay, we have a tank. All right. And so now we have this, here we have this tank, has radius r, and so it's going to have some characteristic thickness of the walls here and on the ends, and we'll assume that the ends and the walls all have the same thickness. It'll have a characteristic thermal conductivity in the walls. There'll be a temperature in the tank, and there's a temperature outside the tank. I'm calling theta 0. Okay, so on the ends, thickness. Okay, then we have area, surface area to work with. So that's pi r squared, and then the conductivity alpha. And then we have the walls. That would be 2 pi r times L would be the surface area. Then we have our conductivity. All right. So how does heat leave? Well, it actually can go out through both ends and the walls. So we'd have the total heat leaving, assuming it's hotter here than it is there. So you have the temperature difference, that drives it. And then I have two resistors. Okay, so we have theta I minus theta O divided by resistance of the end would be the heat flow out of one end. Then the heat flow out of the other end just says multiply by 2. Okay, right? So note, these are not in series. This end spans the temperature inside the tank to the temperature out. So that's why we multiply here by 2. And then we'd have simply the walls, which I called RC anyway, theta I minus theta 0 divided by RC. Okay, and so we just factor them out, and there they are. We'll take a moment and notice that we will generally be dealing with two kinds of sources. An ideal heat supply source, or taking heat out as the refrigerator would do. So an ideal heat source either adds or removes heat at a specific rate. Okay, and then you can have an ideal temperature source. Keeps things at a very specific temperature. Last thing amongst our introductory things we're going to take a look at would be what is the equation for heat in the flow? It's the temperature times the specific heat times the mass flow rate. And that's what we have. There we go. So I will end things right here, and we'll talk more in a moment.